So if you think about it, whenever carbon is reacting with oxygen, eventually what it needs to do to make carbon dioxide is make this molecule here. And it started off with an atom, carbon atom, and an oxygen molecule. So the basically it had to break some bonds. We had to break these bonds, and it had to make these bonds. Okay, so one of the things we need to be aware of is that making energy. I'll just make the text a bit bigger. Actually, I'm going to zoom in. I've given you a massive whiteboard, and I'm just not really using it to its full potential. Let me just zoom. So first of all, we need to note that making bonds releases energy. Oops. And breaking bonds uses energy. Those are the two things, and this relates to the sort of positive, negative confusion whenever you're doing this topic. Which one's positive, which one's negative? And the first thing is to understand these two points. So, making bonds releases energy, and let's color those two in yellow. And breaking bonds uses energy. Okay. So what we're going to do, we're going to be breaking, in order for this reaction to happen, we're going to be breaking this bond, and we're going to be making this bond. So making these bonds is going to release some energy, but breaking these bonds is going to have to require some energy. Maybe I should change that to requires energy. I think that's a nicer word to use. So breaking bonds requires energy. I'm going to have to do that. So now what I happen to know, and if you think about it, you may know as well, is that this is an exothermic reaction. How do we know this is an exothermic reaction? Because this is largely the what happens when we burn most stuff. Really, we're reacting the carbon with the oxygen. Obviously, it's a little bit more complicated than that most of the time, but we know that when we're burning wood, then this is sort of a very simplified version of that reaction. And we know that burning things produces energy, it produces fire, right? So we know that this is going to be exothermic. This is something we just happen to know already, because we just know a little bit about what happens when you react carbon with oxygen, when you burn carbon. That means that because this is exothermic, that means that energy that I put in must be less than the energy I'm getting out. And if I'm having to put energy in to break this bond and I'm getting energy out from making this bond, then these bonds, when they get made, release more energy than these bonds when they get broken. Okay, that's the first thing. We'll sum up that in a moment. I think another thing we need to make clear here as well is, so I'll just add this to this text block here. The other thing to note, the other thing to be aware of is that breaking a bond will be the exact would be let's say exactly opposite the value of making that same bond. What do I mean by that? Well, I mean that let's say it took, I don't know, 300 joules to break that bond. If I wanted to make that bond, it would release 300 joules to do that. Okay, that's another thing to realize here. Okay, so whatever amount of energy I need to use to break it, if I didn't break it and it was already apart and it just snapped together, that's the same amount of energy that will get released when that bond is being made. Okay, So we have these things called, we have a table of bond energies, and we can have a look at the bond energies for this bond here and for this bond here. By the way, another thing to note is that I won't bother writing this down, I'll just explain it. A double O bond, so there are such things as single O bonds, and a double O bond is not twice as much as a single O bond. Okay, they're different, and it'll be the same with this. Okay, so you do need to look at the results, the table, to see what's what. So let's get some table of results, and we'll see of these two. Okay, so here we have a table of bond energies, and let's have a look what are the ones that we are looking for. We're looking for, where is it? We had a C-double-O bond over here, and we had a double O bond here. So notice the unit, it's the amount of kilojoules per mole, right? We've looked at moles before. Remember a mole, by definition, is just simply 6.02 times 10 to the 23 of whatever, right? So it's that many atoms, that many molecules, and now we're talking about it's that many bonds. Okay, so if you had, if we had that many, let's say, that many oxygen molecules, this many oxygen molecules, then you're going to have that many, a mole of oxygen double O bonds. And if I wanted to break a mole of oxygen molecules into separate oxygen atoms just floating about, not bonded, that's how much energy I would need to use to break those bonds, a mole of those bonds. Okay, does that make sense? Now, if on the other hand I had oxygen atoms floating about on their own, they would love to snap together and make molecules, and if I allowed them all to snap together, or if they did all just snap together and make oxygen atoms, a mole of them would release that much energy. So it's that much energy I need to break it, or how much energy it would be need to produce it. So let's say we're just going to keep this simple. We're going to say we had a mole of carbon, a mole of oxygen, and we're going to produce a mole of carbon dioxide. We're going to find out that we're going to break 700. We're going to break. Sorry, what we're going to do? We're going to break this many for a mole of oxygen molecules, so a mole of OO double O bonds, and that means we're going to need to use 498 joules of energy to break it. Okay?
Yep.
Okay, so let's write that down in a post-it note. Okay, so we will need to use 498 kilojoule per mole to break the oxygen. Actually, I think I can do an O. There you go, just use an equal sign. Break the double O bonds. Okay, so that's a useful thing to know. I can't underline, can't make that bold. Let's just change the color of it. Right, so that's how much energy we're going to be needed to break it. And then when we do, we're going to, now, although we're going to make 1 mole of that, notice that in 1 mole, well, in each molecule is going to be 2 of those. So we're actually going to be making 2 moles essentially of these bonds here. So we're going to say we're going to produce. Let's make that one green. Whoops. Okay. So we're going to release 741 times 2. we're going to release 741 kilojoule times 2, which is 1,480. Sometimes the keyboard shortcuts are very useful. Other times you don't really want them to. They just start doing random stuff. Kilojoules per mole. We're going to release that much kilojoules per mole. Okay, so we're going to put this much in. We're going to get that much out. So, how much energy in total would we actually get out? So yeah, that is actually right. So it would. Okay, depends what question I ask, really, I suppose. If I said how much energy is being released, then that would be wrong. But to the question they normally ask, you would do the right one. So if the amount of energy that would be released would be 984 joules per mole, right? If we're going to have to put that much in, but we're going to get loads more out, then the amount released you would take the orange one from the green one. The energy put in, we would take that away from what energy we're going to get out, and we'd get 984 joules per mole, right? However, you're right to take him away in this way, because and presumably that's because you remember from your lessons that what you're going to be doing is going to be working out delta H, which and this is a bit that we always have to think carefully about. So the quick way to know it is that exothermic reactions always have a negative delta H. So that would mean that delta H must be the amount of energy in total you would have to give, you would lose in the reaction, I guess. There is going to be a better definition of it for us, so I'll find that in a moment. But we know that I know that in exothermic reactions, delta H is negative, so it's going to be minus 984 kilojoules per mole. Often what they'll just say is this an exothermic or endothermic reaction? You can do it in terms of, understanding what I've put in, what I've put out, how am I getting something out, am I making a total loss? Then you can define it by that way, or you can do it just entirely mathematically without really fully thinking about it. And if you get a negative delta H, it's exothermic. Okay, so that's a brief overview. I'll just save that.